Hello everyone, my name is Meilong Xu. I'm a PhD candidate at Stony Brook University. Today I will introduce our TopoCellGen, the first diffusion-based framework designed to generate histopathology cell layers with explicit attention to cell topology. This work has been accepted as an oral presentation at CVPR 2025. Cell topology involves two aspects. The first is the intraclass cell distribution. The epithelial cells are usually around the glands and form ring-like structures. The second is the interclass cell relationship. The lymphocytes should mostly surround tumor cells. Then let's clarify why the cell topology is critical. In histopathology, pathologists do not judge cells in isolation. The diagnosis depends who a cell's neighbors are. For example, the ring-like arrangement of epithelial cells around the glands is critical for grading prostate cancer. When this ring-like pattern is distorted, the grade shifts from normal to different grades of malignancy, and this is an important treatment cue. While the density and the distribution of lymphocytes around tumor nests significantly impact survival predictions, these two aspects are critical and should be considered in the generation process. Our primary objective is straightforward. Given only a desired cell count per class, we aim to generate realistic multi-class cell layouts. These layouts should precisely match the target cell counts, faithfully represents individual cell type spatial patterns, and accurately reflects interactions between different cell types. The training pipeline is as follows. Given the target layouts, we first extract the cell counts per class, then pass this count list through an MLP to obtain the cell counts embedding. We gradually add Gaussian noise on the target layouts to obtain the noisy layouts. Then use the cell counts embedding as the condition to guide the denoising process. After obtaining the predicted noise, we formulate the L simple between the Gaussian noise and the predicted noise. From the predicted noise, we can directly approximate the closed form predicted samples, and we enforce the cell counting laws, intra and interspatial consistency laws between the targets and the predicted layouts. Ensuring accurate cell counts at the pixel level is critical. We explicitly enforce pixel level alignments through our cell counting laws. This laws compares binarized predictions with ground truth counts, effectively preserving the correct number of cells for each cell type during the generation. Beyond cell counts, accurate representation of the cell topology, particularly spatial hosts, is crucial for realistic cell layout generation. We capture cell topology using persistent homology. By analyzing the involving topology as we increase the disk radius, we track the birth and death of hosts in the layout. And we represent these events in persistence diagrams. This method allows us to precisely quantify topological structures. The key challenge here is to find the correspondence of the structures between the reference and the synthetic layouts. Our approach matches topological structures between the reference and the synthetic layouts based on our sustained distance. This ensures synthetic layouts maintain consistent spatial patterns both within individual cell classes and across different classes. The intraclass spatial consistency laws ensures that matched structures have similar spatial patterns within the same type of cells. This is achieved by comparing values in class-wise distance transform maps, thereby reinforcing consistent single-class spatial arrangement. In parallel, our method ensures interclass spatial consistency to faithfully represent complex cell interactions. Interclass consistency is enforced through a combined distance transform maps, and that compares spatial patterns of different cell types at the matched locations. And both intra and interspatial consistency losses help us better preserve realistic multi-class cell interactions. Conventional FID measures feature similarity but fails to capture complex spatial cell distributions. To rigorously evaluate the realism of generated layouts, we propose a new metric, topological fracture distance. TopoFD measures discrepancies between the distributions of percent diagrams, focusing specifically on clinically meaningful topological features. Here are the qualitative results. From the results, we can see that our generated cell layouts closely match the reference layouts in both density and spatial arrangement. We conduct experiments on BRCA M2C and lizard datasets and provide our quantitative results on both sample quality and the performance on downstream tasks. Our approach consistently outperforms baseline methods across all metrics on sample quality. In downstream tasks like cell detection and classification, image layout pairs generated by our method substantially improve task performance, confirming both their biological validity and practical usefulness in clinical applications. In conclusion, we presented the first diffusion-based model explicitly for cell topology generation. We introduced a novel topology-aware metric to quantify topological fidelity of synthetic layouts. With our augmented image layout pairs, we enhance the downstream task performance greatly. Thank you so much.